Great.
Right.
Yeah, we can see it. Okay, thanks. So now we have Camilo Heras from IFT, and he's gonna present us about M2 branes, torsion, and gauge supergravities. Okay, Camilo.
Thank you very much, Ignacio. I would like to start by saying thanks to the organizers for this kind invitation and giving me the opportunity to show my work. This was done in collaboration with Maria Pilar Garcia del Moral and Álvaro Restuccia. So the outline of the talk, it is the following. I will start with a brief motivation about our work. Then I will talk about M2 branes, and I will try to establish some differences about what people call classically unstable M2 branes and what we call stable M2 branes. From this time of the talk forward, I will try to restrict myself to what I call stable M2 branes, and I will try to establish some relations of these M2 branes with type 2 big H supergravities and also with PQ strings and the role that torsion plays in the local and global description of these M2 branes. And I will end the talk with a brief summary of our results. So motivation. Gauge supergravities in 9 dimensions with 32 supercharges were classified in this work more than 20 years ago. So we know that in 10 dimensions we have type 2a and type 2b supergravity. There are 4 massive deformations of type 2a supergravity, which are the Romance supergravity and the whole Lambert and West supergravity. And in 9 dimensions, we have one single maximal supergravity, and we have 4 gauge deformations in the type 2a side and 4 gauge deformations in the type 2b side, okay? In this talk, I will restrict myself to this case, which is known as the triplet, because the gauge symmetry group, it is restricted to one of the 1 parameter subgroups of SL2R, okay? So it can be R rotations or hyperbolic rotations. These type 2 big H supergravities have been worked in the literature since more than 30 years ago. From the low energy perspective, it has been found that this supergravity can be obtained by dimensional reduction of type 2b supergravity in 10 dimensions by doing a generalized Scherk-Schwarz reductions, but it can also be obtained by deforming the maximal supergravity in 9 dimensions using the embedding tensor formalism, okay? From the high energy perspective in the literature, there are works that argue that this supergravity should manifest as the low energy limit of a generalized Scherk-Schwarz reductions of type 2b superstring in 10 dimensions, and this should coincide with the formulation of F theory on a twisted 3 torus, where by a twisted 3 torus we are thinking in a torus bundle over a circle with a monodromy which is contained in SL2Z. Therefore, in these 2 approaches, there is a monodromy containing SL2Z. So the question that we want to address is, how can we relate these gauge supergravities from M theory and in particular from M2 branes? Is there any relation that we could find? This question has been addressed in the literature, but I would emphasize that in the last 2 years, we have found some specific links between M2 branes and these gauge supergravities, and I will try to talk about this link in this talk, okay? So from the low energy perspective, we know that the monodromy, it is contained in SL2R, okay? Therefore, it can be classified in one of the conjugacy classes of SL2R according to its trace. Therefore, the monodromy can be parabolic, elliptic, or hyperbolic, okay? The monodromy matrices can be written in this way that we have here in each one of the cases, where the parameters, which are the mass parameters, are, in the case of the parabolic monodromy and for hyperbolic monodromies, are real parameters, while in the case of the elliptic monodromies, it is a compact parameter, okay? And the related gauge groups are rotations and hyperbolic rotations for parabolic, elliptic, and hyperbolic monodromies, respectively, okay? From the high energy picture, we have that the monodromy should be contained in SL2Z, as we all know, but however, we can classify this monodromy in these conjugacy classes according to the value of its trace. Therefore, the corresponding monodromy matrices are given by these monodromies that we have here, where now the mass parameters are restricted to specific values in order for the low energy picture to be consistent with the quantum description, okay? So in the parabolic case, we have that K now are restricted to integer values. In the hyperbolic case, we also have that there are some particular integer values that will be consistent with the quantum description. And in the elliptic case, we have not all the angles will be consistent with the quantum description, but only these angles that we have here, okay? And the relation of these monodromies with the SL2R monodromies are given by similarity transformation in the general case, okay? So from the perspective of F theory on a twisted toroid, we are considering a twisted toroid has a Sold manifold in general that can be understood from the geometric point of view, has a torus bundle over an S1 with a monodromy which is contained in SL2Z. So once again, the monodromy can be parabolic, elliptic, or hyperbolic. In the parabolic case, which is the only case where the twisted toroid is actually an Lie manifold, we have that the Lie group is given by the Heisenberg group in 3 dimensions. But in the elliptic and hyperbolic cases, the Lie group, it is the Euclidean group in 2 dimensions or the Poincaré group. Actually, this was the Sold manifold that was used by Vincent in the previous talk and in his last work to construct the 7-dimensional Sold manifold that he talked about, okay? So in each one of these cases, we know how to compute the first homology group, and we know that there is a non-trivial torsion contribution in the homology, which is directly related with the monodromy of the torus bundle over the circle. So once again, the question that we want to address is how can we see all this from the M2 brane perspective, okay? Is it possible to understand this from the M2 brane perspective? Before continue, let me emphasize that although this twisted toroid has a consistent description, has a torus bundle over a circle with monodromy, the Heisenberg Lie manifold can also be understood as a non-trivial U1 principal bundle over a torus, okay? Where now the K parameter, which was in the monodromy in the torus bundle description here, correspond to the first Chern number. Okay, so now let us talk a little bit about M2 branes, okay? The original formulation of a 2-dimensional membrane evolving in an 11-dimensional space-time that couples to 11-dimensional supergravity was proposed by Bergshov, Seskin, and Tausen in the late 80s. In these times, the supermembrane, how they call it, was like the best candidate to describe microscopical degrees of freedom of M theory, okay? The light congauge Hamiltonian in the flat space was found by David, Hop, and Nicolai in the 88, but a little bit after, they find out, with Lusher and Nicolai, they find out that the SUN regularized model has a continuous spectra, okay? There is a rigorous proof regarding this issue, and basically it means that there is a more rigorous way to understand this, but I will try to talk about the more intuitive argument behind this, and it is that there are string configurations that are instabilities of the theory, okay? In what sense? Well, in the sense that if we build the Hamiltonian of this supermembrane where we have a kinetic term, a bosonic potential, and a fermionic potential, where the bosonic potential can be written in this way, and the XA are basically embedding maps from the worldvolume to the target space, we have that there are certain string configurations which are basically embedding maps such that they depend on only one of the coordinates of the spatial directions of the worldvolume, and these configurations, they make the bosonic potential vanish, okay? So it means that we can start like with an spherical membrane and move along one of the flat directions of the potential, and we could stretch this membrane to an infinite length with no cost of energy, okay? Equivalently, it means that the topology of the membrane or the number of membranes are not preserved in this description, because these spikes are the string configuration that they have no cost of energy. So basically, this implies that this understanding of the membrane, it is classically unstable, okay? De Wit, Peters, and Plewka, they argue that the winding doesn't change the spectral behavior of the theory because there are still string configurations and they are still instabilities of the theory. So winding itself, by itself, does not improve this situation. And because of this, a lot of the community tried to abandon the idea of thinking the supermembrane as an object that could describe quantum degrees of freedom of M theory, okay? And this implies that a lot of the community, well, I mean, we don't know how to understand the quantum, M theory as a quantum theory, okay? Nevertheless, there is a way, well, is there any questions so far? Okay. Nevertheless, there are in the literature some M2 branes that has good quantum properties, has the discreteness of the supersymmetric spectrum, okay? And this is what we call stable M2 branes. The original formulation was done in a target space which is toroidally compactified. And it was rigorously proved that the SUN regularized model has a discrete supersymmetric spectrum. There are string configurations, but they are not instabilities of the theory anymore, okay? So this can be understood in the following way. We have the embedding maps with maps, points of it is a map from the worldvolume to the torus of the target space. We have a standard winding condition, which basically ensures the mapping onto the torus of the target space, where R and tau are moduli of the torus, and L and M are entries of a winding matrix. But there is an additional topological restriction on the embedding maps of the theory that it ensures the non-vanishing feature of the winding number, which is basically the determinant of the winding matrix, okay? So this is a flux condition that implies the presence of a U1 principal bundle, non-trivial, over the worldvolume of the M2 brane. It ensures the appearance of a central charge term in the superalgebra of the theory, and it can be understood as a generalization of the Dirac monopole condition to Riemann surfaces of arbitrary genus, okay? And this N, it is the one that will appear on the winding term of on the mass operator, okay? So non-trivial N implies that there is a winding term in the mass operator. And if you perform a Hodge decomposition on these embedding maps, you will see that the harmonic sector of the embedding map have to always depend on two of the coordinates on the worldvolume. So when you restrict yourself to the string configuration as before, there is at least one term that will be non-vanishing, okay? So there are string configurations, but they are not instabilities of the theory anymore, okay? Therefore, we have, let us say, a consistent way to understand the M2 brane. These classical instabilities are not present if we restrict ourselves to a strictly non-zero winding, okay? So for us, N, the determinant of the winding matrix, cannot be zero in order to have these good quantum properties. But am I saying that we know the quantum description of M theory? Of course not, okay? I'm not saying that. What I am saying is that there are certain particular backgrounds where it can be rigorously proved that the supermembrane have a discrete supersymmetric spectrum with finite multiplicity, okay? Some of those backgrounds are toroidal backgrounds or G2 manifolds, the supermembrane on a PP wave background, which is basically the BMN matrix model, supermembrane with background fluxes, which are fluxes in the target space, and the massive M2 brane on the light cone diagram, okay? In these cases, at least we can ensure that the classical instabilities that were found in the late 80s are not present in the theory, okay? The global description, we will restrict ourselves to the case where we have a toroidal compactification. In that case, the global description, it is given by a twisted torus bundles with monodromy, which means that we have a fiber, which is a Heisenberg-Nil manifold. We have a base manifold, which is a torus related to the special directions of the worldvolume. we have a structure group which are symplectomorphism of the torus of the target space, and we have an application which is the monodromy that goes from the fundamental group of the base manifold to the isotopic classes of symplectomorphism, which is basically SL2Z. Okay, so this is the torus of the target space, this is the torus of the world volume, and this is the U1 associated with the flux condition on the world volume that somehow ensures the non-vanishing feature of the winding number. Okay. Inequivalent twisted torus bundles are classified from a mathematical point of view in terms of the coinvariance, okay? Where Q are basically given by two integers that belongs to the first homology group of the torus of the target space, which are basically the Kaluza-Klein charges. Mg is the monodromy that could reside in one of the subgroups of SL2Z, and Q hat, it is an arbitrary charge, okay? So all charges that are related by this expression, they are associated to the same bundle, okay? According to Kant, these equivalence classes are in one-to-one correspondence with the second cohomology group of the base manifold with twisted coefficients. Okay, so now we will try to stay with this stable M2 branes on a toroidal compactification, and let us try to relate these M2 branes with type 2 big H supergravity and the corresponding PQ strings associated by double dimensional reduction, okay? The first clue that we have regarding the connection with supergravity, it is the following one. When you perform a Hodge decomposition on the embedding maps on the compact sector, you have the harmonic contribution and you have an exact contribution. It can be seen that this exact contribution transform has a symplectic connection under symplectomorphism when you perform the pullback on the base manifold. And this transformation coincides exactly with the transformation of the gauge vector in all type 2 gauge supergravity in 9 dimensions. So not only the type 2b ones, but also the type 2a gauge supergravities in 9 dimensions. So this was like the first clue in order to follow these ideas. So if the monodromy is trivial, let us notice that all this term in the coinvariant just vanish. So it means that the coinvariant only have one element, okay? It means that we have equivalence classes of bundles that contains only one element, and there is, of course, a transformation between the inequivalent bundles, which is basically the SL2Z transformation, okay? The low energy limit in this case is given by type 2 maximal supergravity in 9 dimensions, and the double dimensional reduction reproduces the type 2b SL2Z PQ string on a circle. Actually, the winding and the Kaluza-Klein term of the mass operator was found by Schwarz, but we proved that that particular winding term and that particular Kaluza-Klein operator can only be obtained when you consider the non-vanishing feature on the determinant of the winding matrix, which is guaranteed by the flux condition that we impose. But we also could reproduce the oscillator term in the mass operator, which is related to the membrane excitations, okay, that comes from the Hamiltonian. Nevertheless, the M2 brane can also be consistently defined with a monodromy, which is can be non-trivial. So in that case, we have that the coinvariants, they contains in general more than one element, okay? So it means that we have now certain equivalence classes that they contain more than one element, and of course there is a transformation that it is relating equivalent bundles, and there is a transformation that it is relating inequivalent bundles, and we call them G and U respectively. Both of these transformations, they depends on the monodromy, okay? This is just like a cartoon, but for each monodromy, G and U will have a particular form, and it can be shown that G, it reproduces the gauge symmetry groups for a given monodromy that coincides with the gauge symmetry group of the triplet gauge supergravity that we were interested in studying, okay? An important comment, it is that not only the global description, it is well formulated in the coinvariants, but we were able to extend the Hamiltonian formulation to the coinvariants. So the full theory, local and global, it is formulated in terms of these coinvariants, okay? So a table with our results, it is the following one, where we emphasize the fact that for this monodromy will reproduce the gauge symmetry groups of the type 2b gauge supergravity. These are the transformation between inequivalent bundles that should be associated with what it should be understood as U duality, has a subgroup of SL2Z. And these groups that we have here, it is just the associated to the discrete values that the parameters should have in order to be consistent with the high energy picture. These were found some years ago by Chris Hull and company, and in our case, they are associated to the labels that the inequivalent classes of bundles they have, okay? So what
Camilo,
is the role
you
of,
have 5
sorry.
minutes.
Okay, thank you, Nacho. What is the role of torsion in our description, and what is the relation of this formulation with PQ strings, okay? So in order to understand the role of torsion, at least in the global description, it is a good start to try to identify manifolds with torsion in the global description. So as I introduce the twisted torus bundle, a first guess will be, well, the fiber, it is a parabolic twisted toroid, which is a Heisenberg-Neal manifold, which has a torsion in the homology. And this is right, but we will be particularly interested not in this Neal manifold, but in this Sol manifold, which is considered the torus of the target space fiber over one of the homology cycles of the base manifold. So in that case, we will have a torus bundle over a circle, and the monodromy of this torus bundle will coincide with the monodromy of the M2 brane, okay? So for an M2 brane with parabolic monodromy, we will have a parabolic twisted toroid containing the global picture, okay? So let us focus on this parabolic case for these last slides, okay? So we are considering this parabolic twisted toroid containing the global description. We know the first homology group, and we know that there is a non-trivial torsion cycle. But this is not the only Neal manifold which is contained in the M2 brane global description. Actually, we found that for the outside of the abelian cases, the non-trivial ones, we have the Heisenberg-Neal manifold, and we have also these nilpotent Lie algebras, which are associated with Neal manifolds that are well defined within the global description of the M2 brane. Indeed, you can show that there are a well-defined basis of one forms which are globally defined, satisfying Maurer-Cartan equations in each one of these cases. I will just say that this case in 4 dimensions, it corresponds to primary Kodaira surfaces, and for the case when K it is equal to 1, the primary Kodaira surface, it is a Kodaira-Thurston manifold, okay? And it is defined in terms of the fields of the degrees of freedom of the M2 brane. So I mentioned already that for trivial monodromy, the equivalence classes, they have only one element, okay? And SL2Z, it is a transformation between them. And the inequivalent bundles are classified by this group that we have here that basically correspond to the values that P and Q can have, okay? These P and Q are the Kaluza-Klein charges, and they are related to the values of the PQ string when you perform the double dimensional reduction, okay? However, for parabolic monodromies, we have that we can have K equal to 1, and in that case, we have that the equivalence classes, they contain more than one element, and in equivalent classes, they are classified by the values of Q, okay? But for K greater than 1, you have that each one of the previous equivalence classes, they are split in K elements that they satisfy between each other a cyclic group structure, okay? So you have not only that Q is classifying the inequivalent bundles like here, but you also have that the values of P belongs to the integers mod K, where K, it is the integer related to the monodromy where you are, and it can be checked that for K equal to 0, you reproduce the trivial monodromy case, and for K equal to 1, you reproduce the case with K equal to 1, okay? So if K is equal to 0, double dimensional reduction leads to SL2Z PQ strings on a circle. And if k is different from 0, we have that double dimensional reduction leads to what we call parabolic PQ string that should correspond to some sort of high energy picture of the parabolic gauge supergravity. And in this case, Q, it is restricted to the divisors of the winding number. But of course, once that you consider all possible winding numbers, you will consider all possible values of Q. And P, it is restricted to the integers mod K. Okay. So summary. Coinvariants classifying equivalent M2 brane twisted torus bundles for a given flux and monodromy. We have that the M2 brane with fluxes and monodromy is formulated on the module of Mg coinvariants. The gauge symmetry of type 2b gauge supergravity in D9 is related to the equivalent classes of twisted torus bundle, and the global symmetry of type 2b gauge supergravity is related to the inequivalent classes of twisted torus bundles. And the M2 brane with monodromy includes torsion cycles on the bundle description that I didn't mention that, but for all monodromy, the torsion cycles are on the fiber of the bundle, which is basically the torus of the target space, which is where you are wrapping the M2 brane, okay? And they will contribute on the strings in the double dimensional reduction because you will have membranes wrapping torsion cycles, okay? So like future work, we would like to analyze the role of torsion in the local and global description of these quantum M2 branes for elliptic and hyperbolic monodromies, as well as their corresponding double dimensional reductions. And we would like to prove the conjecture of Chris Hull that he argued that T-duality between the parabolic PQ string should lead to massive type 2A string on a circle. So we would like just to test if we can say something about that. Thank you very much for your attention.
Okay, thanks, Camilo. Is there any question from the audience? If not, in the meantime, I can start asking a question myself. So at the end, you've given that depending on the monodromy, the classes that you obtain, like the theories that you obtain in 9D, you have PQ strings in which the peak and the Q have some restrictions, set P, etc. But my question would be from the PQ7 brane interpretation. Do you have any intuition on how can you see this from like the membrane point of view?
No, I don't have like a formal answer to that question. The only thing that I could say is that in the literature, there are works done years ago about the possibility to consider from the type 2b perspective, 7 branes whose monodromy is not only contained in the parabolic subgroup, like the standard ones that we know from F-theory, but also 7 branes whose monodromy are on the elliptic and hyperbolic subgroup. They find out that for the hyperbolic case, it is not possible to understand a 7 brane solution in type 2b supergravity with hyperbolic monodromy, but actually they found that for the elliptic monodromy, it is possible to understand a 7 brane solution with elliptic monodromy. And if I am not mistaken, in the last of the works where they were trying to research this, they lead to the conclusion that those 7 branes with elliptic monodromy, they correspond to the PQ7 branes stacks that they have elliptic monodromy. Like for example, the E6, E7, and E8 in the ADA classification, they have an elliptic monodromy. And I believe the conclusion of their work, it is that the elliptic 7 branes that they were found from the type 2b perspective correspond to these stacks of PQ7 branes. This is the only thing that I can say now from previous works in the literature.
Okay, thanks, Camilo. So is there any other question from part of the audience? If not, we are gonna still be open now some minutes. So like we're gonna stop the recording so we can do some questions or discussion in more freedom. So if not, and in the meantime, let's give another round of applause to Vincent and Camilo for their very nice presentations. And then, if not, see you all